Have you ever really thought about what goes on behind the scenes with a simple phone call, especially when it's not just phone to phone, but connecting, say, specialized radios, like for emergency services, to a regular landline? It seems simple, but it's actually, well, it's this incredibly complex dance of hardware and software, mostly invisible.
It really is. And that hidden dance, that's exactly what we're getting into today. We're doing a deep dive into Motorola's TETRA telephone interconnect subsystem. This is the tech that lets firefighters, police, utility crews, those professional radio users, connect seamlessly with the outside phone world, whether that's an Office PBX system or the public phone network, the PSTN.
Okay, so our mission today is basically to unpack all of that. We want to
Right.
look at the core parts, figure out how a call actually travels between these like totally different communication worlds, and also explore the control, the security,
Yeah.
all the clever engineering that makes it work. The idea is by the end, you'll have a really solid grasp of this vital but kind of hidden infrastructure.
Exactly. And we're basing this on some solid sources, the technical documentation from Motorola Solutions itself.
Yeah.
We're looking specifically at their TETRA IP compact and TETRA IP scalable systems and how they handle this telephone connection stuff.
Great. So let's start with that main bridge builder, the telephone interconnect subsystem itself. What's its fundamental job?
Well, fundamentally, it's the interface. Think of it as part translator, part gatekeeper. It sits between the TETRA radio network and the external phone network, whatever that might be. It's the piece that actually makes calls possible between a radio and a regular phone.
And the core of that, the real brain, is the Motorola Telephone Interconnect Gateway, the MTIG. I hear it has a couple of really key functions.
Starts with the MTIC. It has two main pivotal jobs. First, audio transcoding. This is absolutely essential. See, radios use a format called ACLP for over-the-air audio. It's efficient. But external phone networks, they need PCM audio. Totally different format. Uncompressed. The MTIG translates between these two back and forth so the audio is clear.
Okay, so that translation, why is it so critical? Are the formats that incompatible, like different languages?
Pretty much, yeah. ACLP is highly compressed, optimized for voice over radio waves. PCM is, well, it's the standard for traditional phone lines, uncompressed, higher fidelity. Trying to mix them without translation would be like, I don't know, trying to play a Blu-ray on a CD player.
Yeah.
Just wouldn't work right.
Yeah.
So the MTIG acts like that universal adapter. Its second big role is handling call control. It manages the setup instructions, the teardown instructions, basically telling the networks how to connect and disconnect the call. It talks between the zone controller in the radio network and the external phone network.
You mentioned the zone controller. What's that? Is it sort of managing things within the radio network side?
Yeah, exactly. The zone controller is the brain for a specific area or zone of the TETRA network. It manages all the radio resources in that zone, figures out routing, and tells the MTIG what to do for call setup. The MTIG is kind of following its lead for the signaling part.
Okay, and I gather there isn't just one type of MTIG. There are different versions.
Correct. There are two main flavors, you could say. You've got the MTIG E1. This one uses QSIG signaling to talk to the PBX. That's a more traditional digital signaling method. Physically, it connects via LAN and also needs an external echo canceller, and it generates tones too.
And the other one, more modern, I assume.
Yes, the MTIG IP, this one is all IP-based. It uses SIP signaling over IP for call control, and the audio uses RTP over IP. Security-wise, it sits behind a firewall or border router, and it has its own host-based firewall too for extra protection. What's interesting is you can't mix E1 and IP types within the same zone. It's one or the other. But you can have both types operating in different zones within the same larger system or cluster.
Huh. That's pretty flexible. It lets you mix and match older and newer tech. Why is that useful? What's the thinking there?
It's about pragmatic upgrades, really. For big organizations, emergency services, utilities, they often have existing E1 connections to their PBX systems. They can't just rip everything out overnight. So this design lets them add new IP capabilities where needed, maybe in new sites, while keeping the older E1 stuff running where it still works fine. It avoids a massive, costly forklift upgrade. It's about evolution, not revolution.
Makes sense. Okay, so the MTIG is central, but you mentioned the echo canceller for the MTIG E1. Sound quality is obviously huge, especially for critical calls. Tell us more about these, let's call them unsung heroes ensuring clear audio. What does the echo canceller do?
Its name says it all, really. It suppresses echo. This echo actually originates in the external telephone network, that slight delay or feedback you sometimes hear on a poor phone line. Without the canceller, that echo gets bounced back to the radio user. Imagine trying to talk while hearing your own voice delayed. It's incredibly disruptive.
Oh, I can picture that. especially in an emergency, trying to give instructions while fighting your own echo. Nightmare. So where does this device actually sit in the chain?
It's placed right on the E1 link between the MTIG E1 gateway and the PayVX owned by the customer. And it's a standalone box. It doesn't need any control signals from the zone controller, which simplifies things. It has its own configuration tool, something called WinMata Forza.
Standalone. Interesting. Good for resilience, I suppose. Now, what about the Enhanced Telephone Gateway, the ETG? Sounds like something for bigger systems.
That's exactly right. The ETG is basically a specialized PayVX itself. It works together with the TETRA system's call routing features to provide connections to multiple external networks. Think about a situation where one TETRA system is shared by, say, police, fire, and public works. Each might have its own separate PayVX. The ETG acts as the central hub to connect the radio system to all those different phone networks, plus maybe the public PSTN directly.
Ah, okay. So for these big shared radio systems, the ETG is like the main telephone exchange handling all the different external lines.
You got it. It's essential for those shared network scenarios. It centralizes all those connections and manages the complex routing needed to get calls to the right place.
Okay, we've seen the pieces, the MTIG, the canceller, the ETG. Now, how do they actually work together? Let's follow a call. Say, a paramedic needs to call the hospital ER from their radio. How does that happen? First off, what kinds of calls are even possible?
The system supports calls from a radio to a landline, and calls from a landline to a specific radio, direct one-to-one calls. What it explicitly does not support is interconnect calls going to or from a talk group. It has to be an individual radio.
Got it. Individual calls only. So let's trace that radio to landline call. The paramedic dials the hospital number. Then what?
Okay, so the user dials the digits. The radio sends that request over the control channel to the system. First, the system checks. Is this radio even allowed to make phone calls? Authorization check. Then it figures out which zone's MTIG should handle this call, usually the one the radio is currently in.
And then it starts grabbing the necessary resources, right? Like finding a free path.
Exactly. It assigns resources. The radio side channel, a gateway router, the MTIG itself. The zone controller sends out multicast addresses, basically instructions for setting up the audio path. The MTIG and the radio site join this audio path. Before connecting outwards, the system checks the number against dialing restrictions. Is this number allowed? Then it selects a PX to PSTN resource. Think of it like grabbing an outside line from the PBX. The PX initiates the call out to the hospital's number on the public network. Finally, the radio gets its traffic channel granted, switches to it, and the paramedic hears the phone ringing.
That PX to PSTN resource selection, just to make that concrete for listeners, is that like finding a free physical line or a channel? What's being selected?
Good question. It's essentially securing an available outgoing trunk connection. Think of it like finding an open lane on the highway leading from the internal phone system, PEX, out to the public network, PSTN. If all those outgoing connections or trunks are busy, the call can't go out, even if the radio side is ready.
That's quite a chain reaction. What happens if something goes wrong if a call can't connect?
Well, a few things can happen. If all the radio channels are busy, or if all the MTIGs are busy, the call might get put in a queue. Sometimes, a radio might be programmed specifically not to allow phone calls, or only to specific numbers, so the attempt might be blocked right away. And there's a hard limit based on licenses. The number of simultaneous calls is capped by how many MTIG licenses the system has. Run out of licenses, no more calls.
So physical limits, permission limits, and license limits. Okay. What about the other way? Landline to radio. Is that simpler?
Yes, quite a bit simpler for the caller. Someone on a phone dials a specific access number linked to the TETRA system, and then usually the radio's number. The system takes that incoming call, automatically finds where the target radio is currently registered, assuming it's on a main trunking site, and routes the call directly to it, no matter which zone it's in.
Okay, so the call is connected. How long can it last, and how does it end?
Once the call is up, the radio is on a dedicated traffic channel. The system keeps track of how long the call has been going. There's usually a configurable timer, a maximum call duration limit. If the call hits that limit, or if a higher priority call comes in, like an emergency group call, the system can automatically terminate the interconnect call. There's usually a warning tone played to both users shortly before it cuts off, so it's not abrupt. It's about managing resources.
Right, keeping those critical channels free. Now, mobility is key for radio users. What if our paramedic is on that hospital call and drives out of range of the current radio site? Does the call drop instantly?
It's handled quite smartly. If the call is already active and they move to a new site, if the new site has resources free and available channel and interconnect capability, the call just hands over seamlessly. granted immediately. If the new site is busy, the call gets queued for about 5 seconds. If a resource frees up in that window, great, the call continues. If not, after 5 seconds, the call is dropped. And interestingly, the person on the landline doesn't get any notification that the call dropped due to roaming issues.
Okay, so the radio user might just suddenly lose the call after 5 seconds of maybe silence or garble.
Pretty much. Silence is typical while it's trying to reestablish. Then, if unsuccessful, the call just ends on the radio side. It prioritizes freeing up the radio resource quickly if the handover fails.
And if they roam while the call is still being set up, like while it's ringing?
In that case, if they roam to a new site during the ringing phase or while the request is queued and the necessary resources aren't immediately available at the new site, the call attempt is just dropped right away. No queuing in that scenario.
That's some detailed logic to keep things running smoothly, or at least predictably. Okay, let's shift focus a bit to control, configuration, and security. It begs the question, why would you even want to limit telephone calls? Wouldn't maximum connectivity always be best?
That's a really insightful question. You'd think so, but it comes down to resources. These interconnect calls are resource hungry. Each one ties up a dedicated radio channel, often for much longer than a quick push-to-talk radio call. Plus, calls to the outside world can incur actual costs, poll charges. So, limiting them isn't just about saving money, it's about ensuring that the primary function, critical radio-to-radio communication, always has the resources it needs. You don't want routine phone calls blocking an emergency broadcast.
Resource management, okay.
Thank you.
So how do system administrators actually apply these limits, I guess, at different levels?
Exactly. You can control it at the individual radio or user level. That's under the User Configuration Manager, the UCM. You can set a radio to, say, only receive calls, not make them, or only allow calls to a predefined list of numbers. You can even set limits like maximum total call time per month for a specific user. And each radio gets an interconnect profile with a priority level usually 2 to 10. Priority 1 is reserved just for emergency calls, so they always get precedence.
And what about broader controls for the whole system or a specific site? Using the ZCM, the Zone Configuration Manager.
Yes, the ECM allows for infrastructure-level controls. There's a feature called Table-Driven Shared Service. This lets managers define, for each site, how many interconnect calls can be active at any given time, and maybe even limit their duration, often in 2-hour blocks throughout the day. And there's that global maximum interconnect call duration timer we mentioned, which applies zone-wide, with the warning tone before cutoff. It's all about fine-grained control.
Okay, that's quite detailed. Now, something you touched on earlier was tones. The MTIG generates them. This seems surprisingly powerful. What kinds of tones are we talking about?
It's more than just ringing. The MTIG can generate a few types. Sequence tones, a series of specific tones and pauses. Continuous tones, plays on and on until stopped or timed out. DTMF tones, the standard touch tones you use on a phone keypad, 09, star, hash, even AD. And for the MTIG IP version, it can even play wave audio files like pre-recorded announcements or alerts.
Wow, actual audio files, so you could have custom alerts.
Exactly. The system comes with predefined tones for things like ringing, queuing, the call end warning, and all the DTMF digits. But the really clever part about DTMF generation is that the digital radios themselves often can't produce those tones. So if a radio user needs to interact with an automated system on the phone network, like punching in options for voicemail or an IVR, they rely on the MTIG to generate those tones for them based on their keypad presses. Without it, they'd be stuck.
That's a neat solution to a hardware limitation. Very clever. And sticking with the MTIG IP, what about its security? Dealing with IP networks always raises security questions. Is there a built-in firewall?
Yes, absolutely. Security is key. The MTIG IP has an integrated firewall. It uses a neat system with 2 rule sets, an operational OP set, which is currently active, and a non-operational NOP set. When you need to make changes, you edit the NOP set. Then you activate it, which swaps them. The NOP becomes the new OP, and the old OP becomes the NOP. This is fantastic, because if you make a mistake in your new rules, you can instantly swap back to the previous known good configuration. It minimizes risk and downtime.
Ah, like having an instant undo button for your firewall rules. Very smart for critical systems. Is that common practice?
It's definitely a best practice in critical infrastructure. The thinking is you absolutely cannot afford to accidentally lock yourself out or break connectivity while updating security rules. This OP and OP swap provides that crucial safety net. Downtime in these systems can have, very serious consequences.
Understood. Okay, let's zoom out a bit to the overall network structure, the grand design. You mentioned private versus shared networks earlier. Can you recap the difference?
Sure. Private networks are generally simpler. They might connect the dimeter system to just one PABX, or maybe a few closely related PABXs belonging to a single organization. Shared networks are typically larger and more complex. They connect the Demetra system to PABXs belonging to multiple, often independent organizations, all sharing the radio infrastructure. Plus, they usually connect to the PSTN. These shared setups are where you absolutely need that enhanced telephone gateway, the ETG, to handle the diverse connections.
Right, the ETG as the central hub. So, in these complex networks, how does a call actually find its way? You mentioned call routes acting like GPS.
Exactly. Call routes are the key to navigation here, especially with an ETG involved. For a call going out from a radio, the zone controller looks at the number dialed and adds special routing digits, the outgoing prefix. This prefix acts like instructions for the ETG, telling it which specific PBX to send the call to, or if it should go out to the public network. For calls coming in from a landline, the ETG adds an incoming prefix to the number that was called. The zone controller uses this incoming prefix to figure out which external network the call came from, maybe for validation or special handling.
So, these prefixes are like little labels telling the system where the call came from and where it needs to go. What happens in a big system with multiple zones? If a call starts in a zone that doesn't have an ETG, is it stuck?
Nope, they thought of that. They use redirect call routes. If a call originates in a zone without its own ETG connection but needs one, the system can automatically reroute the call setup through a different zone that is connected to an ETG. It adds flexibility, ensures calls can still get out even if a local zone isn't directly connected.
Very resilient. Now, how does the system identify the specific radio being called from a landline? How does it translate a phone number into a radio ID?
There are basically two ways to address a radio. One is using a direct dial-in DDI number. This looks like a regular phone number, potentially quite long, up to 15 digits. Each radio can be assigned a unique DDI. The system can be configured cleverly, though. It might only look at, say, the last 4 digits of the DDI to actually identify the radio internally. Makes dialing potentially easier while still allowing unique external numbers.
Okay, so DDI is like its public phone number. What's the other way? You mentioned ISI.
Right, the ISSI, Individual Short Subscriber Identity. That's the radio's unique internal ID within the Demetra system itself. To tell the difference when a number is dialed, the system uses a configurable radio ID prefix. So, for example, you might configure 99 as the prefix. So if someone dials 99 followed by the radio's ISSI, the system knows, they're dialing the internal radio ID directly, not a DDI phone number. It helps distinguish the two.
That makes sense. And with all this complexity, controlling who can call whom must be important. How granular can the call barring get?
Very granular. The system uses something called exclusion classes. Each exclusion class defines patterns of numbers, disallowed dialing patterns. These can be prefixes, full numbers, ranges. You can define patterns that users cannot call and patterns from which users cannot receive calls. You can have up to 15 different exclusion classes, and each class can contain up to 16 of these disallowed number patterns, each up to 15 digits long. So you can get incredibly specific about blocking certain types of calls, like international numbers, premium rate numbers, or calls between specific agencies if needed.
Wow, that's some serious control. Okay, but even with the best design and configuration, things fail. What happens if, say, an MTIG gateway just stops working? What are the common failure points?
Well, if an MTIG fails, the impact depends on the setup. In a system with multiple MTIGs, maybe spread across zones, the failure of one might be almost invisible to users. Other MTIGs can often pick up the load thanks to that redirection capability. If it's the only MTIG in a zone or system, then obviously telephone interconnect calls will stop working through that gateway. But crucially, other radio functions push to talk, group calls, dispatchments, they usually keep working fine. The core radio communication isn't typically affected. Calls can also fail simply because no suitable radio channels are available. They might be busy with other calls, switched off for maintenance, or actually failed themselves.
So if a user reports problems, I can't make phone calls, where does a technician start looking? What are the first troubleshooting steps?
Good practice is always to check the basics first. Verify audio in both directions if possible. Can radio call landline, ND landline call radio? Or does it fail only one way? Then check the system monitoring tools, like the Unified Event Manager, UEM. Look at the MTIG status. Is it showing active? Is the severity clear? Also check the UEM alarms for specific error messages. Things like MTIG initializing are usually normal startup messages. Just wait. MTIG service not active probably means the MTIG server process needs restarting. An unstable PABX link detected message points towards checking the physical connection, the IP settings, address, subnet mask, or maybe username password issues if it's an IP link. Basic connectivity checks.
Okay, what if the basic status seems okay, but calls just won't connect at all? No ring, nothing.
If calls aren't even initiating, you need to dive into the configuration details. Check the specific radio's profile. Does it have the correct telephone gateway ID assigned? Check the main interconnect subsystem settings in the configuration manager. Things like the radio ID prefix, number of DDI digit setting, are they correct? Definitely verify the call route definitions. Do they point to the right gateway ID? Are the outgoing and incoming prefixes defined correctly? Make sure the user profile actually has interconnect enabled. And a really critical one for MTIP. Double-check the public IP address configured for the signaling stream in the MTIC object. That's how the call setup messages travel. If that's wrong, the call won't even start.
Right, the signaling path. And what about that really annoying problem? The call connects, you can hear it ring, maybe the other person picks up, but there's just dead air. No audio either way. So the classic connected but no audio problem. That almost always points to an issue with the media stream path. Specifically, in the empty object configuration, you need to check the public IP address defined for the media stream. That's the IP address where the actual voice packets, RTP, are supposed to flow. If that's wrong, or if a firewall is blocking traffic from that address and port range, the signaling will work, the call connects, but the audio itself has nowhere to go. So, silence. So signaling IP for call setup, media IP for the actual voice.
Got it.
Wow, we have really covered a lot of ground here, gone deep into this Motorola Dry-Mitra telephone interconnect subsystem. It's clear that bridging radios and phones isn't simple at all. It's this really sophisticated mix of hardware, complex software rules, routing logic, security, all working together. It really highlights the layers of engineering behind things we might take for granted.
Absolutely. What stands out is the sheer amount of thought that goes into managing resources, ensuring quality, providing security, and maintaining resilience. All that complexity is hidden from the end user, who just wants to make a call. But it's all humming away in the background, making sure critical communications work reliably across different network types.
So maybe a final thought for you, our listeners. The next time you make any kind of call, especially if you suspect it might be crossing between different types of networks, just take a second to consider the unseen complexity making it happen. What other hidden layers of engineering are powering the simple actions we perform every day in our connected world? And maybe how does understanding a bit about those layers change how you view the technology you use? Something to think about.